Okay, hello everybody. My name's Sammy. This is for MAT 4906, Advanced Topics in Operations Research. And I'm going to be going over Chapter 12, Review of Calculus and Probability from Winston's text. This is just going to be a chapter. It has 7 sections, basically an overview of all the calculus and probability you would need for the next few chapters. So it's kind of weird because most of these sections you're not going to completely get what it's going to be used for later until the last few sections when I show you how to use Excel and whatnot with probability. But if you think about it, when we're goal programming, integer programming, creating models, and simulations, we're trying to understand how, or whatever our constraints are, they are going to be dependent on probability. So the availability of goods is also dependent on the likelihood of certain events happening. Having food is dependent on whether or not we have a good rainfall that year. So there's a lot of factors that go into goal programming that also use calculus and probability. And without further ado, I'm going to start section 1. I'm going to do a video for each section and they'll be compiled as one video. But so if you can only watch one section at a time, I'm not going through the whole thing at once. So this is just a review of integral calculus for the first section. Indefinite integral. Basically, all you have to worry about is that there are these two functions that are related. Little f of x is the derivative of big f of x. So we say f of x is the indefinite integral of little f of x. And here's the mathematical representation below. You've probably seen it a million times in your textbooks. Basically all I say is integrating is backwards derivative. And if that helps you, great. But however you remember it works as well. So the rules is basically the most important part of this definition. The first one, if you notice, we always add our plus c. These, I would say, are super important because they're pretty standard. I mean, you see e to the x and exponential functions quite a bit. Removing constants, all those things are great practice for when you're evaluating integrals. The last 4, they're kind of funky. I wouldn't say they're the most common. I think they're just giving you rules for if you encounter a wonky integral and you don't feel like solving it for 4 pages. Most integrals you can do multiple different ways. There are different techniques. One of the main techniques that you see a lot is integration by parts. And it's if we have 2 functions, u of x and v of, it could be any 2, but usually the standard is we use u and v. And we can't evaluate it when it's multiplied together. I kind of tell people to think of it as like the chain rule of integration. You can't just evaluate it all together at once. So we must use integration by parts. This is the general formula, but I basically just tell people you can remember it as u dv equals uv minus v du. And you don't even need to worry about that first part, like just this. If you memorize that, you're good to go. So, and u and v are the functions, du or dv are going to be their derivatives. So now, probably one of the most important definitions would be the definite integral, because most of the time in this book, we are actually dealing with real life things, real numbers, stuff that is tangible and not indefinite. So I put this figure in here because if you notice, we're trying to represent a function as area almost, and the definite integral takes all these little rectangles of area and approximates the area under the curve, and that allows us to find the definite integral. So as we work through these, just kind of keep this figure in mind that we are approximating area technically. And, this definition is big and long and wordy, but basically the most important parts to pick out of it, I would say, are continuous function, and it needs to be on an interval. That function needs to be continuous for all the points on that interval. So if there's a hole, you would have to do 2 separate integrals. You couldn't do it for that entire curve. And then this right here is pretty important. So x of 0 equals a, and then all these little rectangles above here, x1, x2, and x3, we're just adding delta each time to get these rectangles until we get to b. So if you notice, I add delta every time until I get to b. So we start at A, we go to B, and we're adding delta each time to get our x1 point, our x2 point, and so on. And I want to point out right here that delta is B minus A over N. Okay, so as delta approaches 0, or wherever we started, N is going to grow larger. And if we take all this, we can sum up those rectangles, if you notice, as delta approaches 0 right here. So f of xi, so that's each point. So it could be f of x1, f of x2. The curve is going to be different at each point. And then we multiply it by delta because that gives us that fair stepping rate to go at for each rectangle. And then we will finish with our actual definite integral definition. So basically, this is the same thing as the summation, just represented differently. And the definite integral plays a large part in our first theorem, which is the fundamental theorem of calculus. Very important. It basically just sums up everything we just went over. It has to satisfy the two things. F of x is continuous, and it's on this interval. Those are the two most important things before you even can evaluate the integral. And if you notice, we just evaluate it like we normally would, but instead of the indefinite way, we now plug in those values and subtract them. So I'm going to go over an example, its solution, and then we'll try a problem together. Suppose that at time t measured in hours and the present t equals 0, the rate at a of t at which customers enter a bank is a of t equals 100t. During the next 2 hours, how many customers will enter the bank? Okay. So basically, if you notice, we first start off with saying let t of the blah, 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 blah equal 2. This is a fancy way of saying our interval is going between 0 and 2. Because our initial, we were told, was 0. We were told that only 2 hours pass. So the important part now is we need to know delta, which is 2 over n. And if you guys remember from above, delta is b minus a over n. So we also need to know between time t of I minus 1 and ti that these amount of customers enter the building. So we have our summation below as x is going to 0. We are summing up basically all these little triangles under our curve of 100t. So using the fundamental theorem of calculus, we can take that summation and put it into the integral. And if you notice, the really only different thing about this is that we have numbers on the integral sign now. That's our time 0, our time 2, our function. We evaluate it using the power rule for integration. So if you recall from above, it's x to the n. If you evaluate it, you get x to the n plus 1 over n plus 1. So that's how we got 50t squared. Plugging in those numbers, we know that 200 customers will now enter the bank. So this solution was pretty in-depth. What I would say is for the one we're going to do, like here is the most important part. I mean, that's where I normally start. I don't think you need to necessarily go into the great detail. So I'm going to read our problem. The present is t equals 0. At a time t years from now, I earn income at a rate of e to the 2t. How much money do I earn during the next 5 years? Okay, so they gave us all the information. We have our t equals 0. They say that's the present or the initial. At time t years from now, okay, so that is our variable t. I earn income at a rate of e to the 2t. So a rate of time, or what income, is a function of time. So I'm going to call it f of t. And they told us that it's e of t. So normally, whatever function they give you, that's just your function. It's not sneaky. It's pretty straightforward. And then we want to know how much money I'm going to earn during the next 5 years. Okay, 5. So they gave us a duration, so that probably means that our x, or t, is between 0 and 5, correct? That is the interval. Our function is continuous along that interval, so we are allowed to use the fundamental theorem of calculus. I also am going to point out our delta would be 5 minus 0 over n, or 5 over n. So that would be the increment that we're stepping from t to the 1 to t to the 2 to t to the 3, and so on our little curve. So I'm just going to, like we did above, using the formula, our limit's always going to 0, and our summation will always go from I equals 1 to I equals n. And we don't have 100 ti, though. We have e to the 2t underscore I. And we are multiplying that by our delta, which was 5 over n. And if I put that in the integral form, we're going from 0 to 5. We put our function in with the corresponding notation. And basically, fundamental theorem of calculus says we just evaluate this normally to start. So I'm going to use, there is a rule up here, right, with e of the x. E to the x does not change, as we know. So you just put the coefficient as the fraction, basically. So I would have e to the 2t over its coefficient, because if you were to take the derivative, it would end up back at e of the 2t. And this is also for an integral of 0 to 5. So like above, we just plug in the values. So we're plugging in f of b minus f of a. I'm just going to write that over top so we remember. So e 2 times 5 over 2 minus e 2 times 0 over 2. And I know a lot of times we don't always evaluate for 0, but when it comes to e or any sort of exponentials, I would highly suggest putting the 0 in, just in case. So this would leave me with e to the 10th minus e to the 0. They're both over 2, so we're just going to put them both over there. E to the 0 is 1, so cleaning that up, I will earn this much money in 5 years. I'm sure if you did it on your calculator, you will get some sort of decimal, but this is what you would accrue in 5 years based on that income rate. So that's kind of just a little review of integral calculus and how we would solve this for problems later in the book. Thank you guys for watching the first section. If you're doing the next section with me, just wait, and another video will pop up for 12.2. Okay, thank you. Bye-bye.